All right, so good morning and welcome to this video on the topic of N-type semiconductor. See, N-type semiconductor has a lot of details which you may not be aware of, and many students are confused because of the diagrams, especially the energy diagrams which they see. Today, my aim is to clear those doubts in your mind with the help of those diagrams. So let's start discussing N-type semiconductors. Now, as you know, N-type semiconductors, and I'll just start with the basics. So, N-type semiconductor essentially means N-type semiconductor. How do you create it? Semiconductor is created. What you do is you pick up a, so these are also called as extrinsic, okay, impure semiconductors. I'm sure you know, but I'll just repeat extrinsic or impure semiconductors, okay, semiconductors. And the way they work is they have an excess electron, okay, they have an excess electron. The excess electron concentration is more, and that is what makes them N. N is negative. And so these are the basic things you must know. But apart from, so these are the majority carriers. These are the majority carriers in the case of N-type semiconductors. Okay, so these are N-type semiconductors, and electrons, the excess electrons are the majority carriers. But there are some minority carriers also, which are holes. They're very small in number, and we will discuss, what goes on in this. So this is, if you know this, you know only about definition. You have no clue about the detailing of semiconductors. So let me just give you an insight into the detailing of semiconductors. So what you do is you pick up a pure semiconductor. You pick up a pure semiconductor, okay? And I will just write semiconductor as SC. You dope it with some impurity, okay? You dope it. This impurity for N type is a pentavalent, pentavalent impurity, okay? If you add a pentavalent impurity is when you are able to create an N type, okay? And of course, I will create a separate video for P type, because the detailing I will do is very different than what you would have seen anywhere else, okay? And this is going to be a memorable experience for you. So when you add a dopant, which is a pentavalent dopant, what you create is an N-type semiconductor, okay? And all right, I hope this is clear in your mind that what we have created is an N-type semiconductor with the help of a pentavalent. So phosphorus is an example, okay? So phosphorus is an example of a pentavalent impurity. So at a atomic level, what goes inside a N-type semiconductor? Let me just give you an insight into that. Okay, so this is what goes into it. You have what you do is you pick up a pure semiconductor like silicon. Okay, you pick up a silicon type of semiconductor, and what we do is we, using the process of doping, we add a pentavalent impurity. I'll just draw the atomic level diagram so that it is clear. So this is your silicon, this is silicon, and this is silicon. This is silicon. You would have seen similar diagram in my previous videos. I'm just modifying that. What I do is I add a pentavalent impurity like phosphorus in this. Now phosphorus, when it enters, it creates bonding with the silicon. Okay, so these are the bondings being created by the phosphorus. Okay, obviously phosphorus is 5 plus because it has the, okay, so it has pentavalent, right? So P, it is always P5 plus, and silicon, has only 4 electrons to bond with. So This is 4 plus generally, so it can bond with other 4. Here, when impurity is added, so the bonding is done. Okay, so these are the bonds that get created. Okay, I think the diagram was not good, but let me just correct it. Okay, so silicon, okay, silicon. I'll just use a different color to show you how silicon looks. Okay, so this is silicon. Okay, this is silicon. This is silicon. This is silicon. Okay, and then what happens is in the middle, what I'm showing you is phosphorus. So I'm just doing it so that it's easy for you to understand. I'll just enlarge the diagram also so that you can see what's happening. Okay, so the bond creation is happening, and you can see, since phosphorus has 5 electrons, 1 electron is always extra with it. Okay, so the bonding, so 1 electron comes from phosphorus, the other comes from silicon. Okay, I hope this is visible to you now, and more clear in your mind. Okay, so I will just reduce the size of the dots which I'm using. You can use, 1 electron is coming from silicon, the other is coming from phosphorus, and same holds true for this bond. Okay, so one comes from, the other one comes from silicon, and so on and so forth. So you can see the phosphorus in the middle, okay, has used a 4 electron. So what it is left with is 1 electron, which is free. And so what happens is when you, so if you talk about 0 Kelvin, okay, so if the temperature is 0 Kelvin, that electron, which is the extra electron of phosphorus. So let's say, let me show the extra electron of phosphorus with this color. Okay, so this particular electron does not, move from the valence band to the conduction band. But we'll come to that. I will correct myself here. I will just say that this electron is here. It is still attached to its basic phosphorus atom at 0 Kelvin. At 0 Kelvin, this is the situation. All right. Now let me just do a comparison, and I will go into detail of this energy diagram, which I promised I will. But listen to this patiently so that you're able to understand what's happening here. All right. So let me just draw the diagram of another situation where the same situation, but now the temperature is 273 Kelvin. Okay, so the temperature is, I'm sorry, the temperature is 300 Kelvins. Okay, I meant 27 degrees or 300 Kelvin. So this essentially room temperature is being discussed. So this is situation number A, and this is my situation number B. So these are the two situations we will compare from atomic point of view, and then we will start going in detail of each one of them. So let me just draw the diagram. So this is my phosphorus again. All right, this is my silicon. Let me just cover this like this, and then of course phosphorus. Let me draw silicon. Let me draw silicon. Let me draw a silicon. So this is the situation now, and so this is the way it looks, and the silicon, and silicon, and of course I will show you the bonds as usual. Nothing great about it. So there is an electron which comes from this side, and then this is the dot from. Sorry, I don't know. Let me just use a different font here. So let me just. This is the electron that comes from silicon. Okay, silicon, phosphorus. This is from phosphorus. Phosphorus, silicon, phosphorus, silicon. These are the covalent bonds being created. We can, show also the covalent bond, the electrons are being shared, and, overall 8 electrons are there. But I told you phosphorus has a separate electron, an extra electron, because it's pentavalent, 5 plus, right? So the electron which we had drawn here, right? This electron specifically, this electron, which is a phosphorus electron, this electron now gets energy, which is thermal energy, because you have the temperature as 300 Kelvin. This 300 Kelvin will excite this extra electron. And this electron, which is the extra electron, now becomes extra in the lattice of silicon. Okay, so it is able to move around because of the thermal excitation you gave it, right? So therefore there is an excess electron in the end. So what you have done, so this was an n-type semiconductor. Yes, it was a n-type semiconductor, but this is at 0 Kelvin, right? It still doesn't work like n-type semiconductor. But when the temperature is room temperature, then starts the magic of extra electron. So at 300 Kelvin or higher temperatures, the concentration of electrons keeps on increasing, and then it leaves behind a phosphorus ion with only 4 plus. One electron is lost to the lattice. And now this is the comparison between the two diagrams. One diagram at 0 Kelvin, the other diagram at 300 Kelvin. But let me go, as I told you, this is not about understanding what are n-type electrons. So if you just know n-type electron is the created by adding some phosphorus or a pentavalent. Specifically, I'm talking about antimony. Sorry, the n-type semiconductors. That is not the case. So the real detail will come now, which is where you get confused, and no one has bothered to explain this, in the whole of what should I say, the family of platforms that you have, or whatever. So let's talk about the energy diagrams now, which is where this whole concept will become very clear in your mind as to what goes on at the energy level. And then once you hear me out, you are never going to forget how to look at a n-type semiconductor. So this is going to be very special. Okay, let me just draw the diagrams and explain you. Okay, so this is your situation, and let me just draw the diagram. Okay, so this is the diagram. Okay, so this is your the valence band, and then of course you always have a forbidden gap. And I'm drawing this diagram again for 0 Kelvin. So I am drawing the diagram of this state, which is 0 Kelvin. Okay, so and of course then you have your uh, the conduction band, right? So all the electrons generally are in the valence band. So I will just draw the electrons are in the valence band. Okay, this is the valence band. This, and I'm drawing and you can draw the electrons, right? So these are the electrons in the valence band. So this is your valence band. This is your energy gap, and this of course is your conduction gap. Your aim is always that the electrons in the valence band, they jump and reach the conduction gap. And let's see, at 0 Kelvin you will not be able to achieve this movement of electrons from valence band. So these are electrons. Okay, let me just label it for simplicity. See, these are electrons. Okay, now just complete the diagram a bit so that the band looks like a band actually, right? So let me just draw a line here and show you that this is a band we are referring to. So this is a band. Okay, then there is an energy gap we have drawn, and this is your conduction band. Okay, so the conduction band is also there. When you do the doping, the level of energy which is available with the phosphorus is somewhere here. Okay, let's draw the level of energy of the phosphorus, because doping, you have to, if you have to complete the energy diagram, you must show the energy level of the phosphorus. So if you talk about phosphorus which you added, the energy level is slightly below the start of the conduction band. Okay, so this is your conduction band start, right? This is where it starts, slightly below that. Now what you have done so far is, this is 0 Kelvin temperature. At 0 Kelvin, the electron which is available with the phosphorus, okay, so the extra electron which we discussed, which is available with phosphorus or any pentavalent impurity, will not be able to reach the conduction band. So this is your conduction band. Nothing is going to happen at 0 Kelvin. Okay, so this is your, so even though you added n-type semiconductor, nothing is happening. You think you've just added a phosphorus, and you have created definitely an energy level. This energy is called as a donor energy level and is generally represented by E donor. Okay, this is E donor. The phosphorus, which I mentioned, acts as a donor of electron, right? You would have seen in the atomic diagram that it donated an electron to the, so it's a donor kind of situation. Let's talk about, now this is 0 Kelvin, nothing is happening. The electron from valence band, or the silicon electrons are not able to reach the conduction band. The electrons available to phosphorus, which I just show you here, very close to conduction band, they've created a donor level energy. It's called donor level energy, or energy level of the donor. These electrons are also not able to jump across and reach the conduction band. Now let's talk about a situation when the diagram is slightly changed and the temperature now becomes what? The temperature becomes to the tune of 300 Kelvin. Okay, so the room temperature. Let me just draw the equivalent diagram of this. Again, I will use the banding. Okay, I will draw the bands, but this time something is going to happen. Remember, this new diagram is for a different temperature now. Okay, so let's say, and don't go by the, so I'm trying to make it as close to the left one, but if I'm not able to do that, it's okay. Okay, so let me start here because I have little space left. Let me just shift the attention and take you here. So all right, so I think this is better. This looks good. All right, so the first level obviously is the valence band. So let's say we have created the valence band. So this is our valence band, and the electrons, silicon electrons are here, right? So what I've drawn is a valence band below. The first band has been created. The second, then you have obviously an energy gap. So energy gap also is created. This is your energy gap. And then what are we going to do? We are going to create a conduction band also. Okay, so a conduction band, which I'm trying to make it, as close to the left hand side figure. But remember, the diagram now is being drawn at 300 Kelvin, which is a room temperature. And of course, I also need to draw the energy level of the donor energy level, which is phosphorus. So let me just draw it along the previous diagram. So this is it. So this is your conduction band, the start of the conduction band, which is your EC, let's call it EC here, right? So this is your EC, and this is your ED, the donor, and of course this is your EV, which is the valence. Okay, so the electrons which are residing in the silicon, okay, these electrons, okay, these are the electrons. And if you remember the previous video on intrinsic semiconductors, what did you notice? At the moment the temperature touches 300 Kelvin, these silicon atoms, they are able to send some of the electrons to the conduction band. Okay, so this is your conduction band, right? So the conduction bands ends here and starts from this point. Okay, so some electrons reach the conduction band from the silicon. So this is the valence band of the silicon. So this is the valence band of the silicon. And then some electrons which are here, okay, these electrons are here, they belong to phosphorus. They also get thermally excited because of the temperature. They are able to reach here very easily because the gap is very small. So this is a very small gap, okay, small gap, right? And that's a beauty, that the moment you add a dopant, just adding the dopant is not enough. When you add the dopant, the energy level of the dopant has to be very close to the conduction band. If it is not so, then the dopant will not work. And that's an impression a lot of students have, that by adding an impurity or doping, this will happen. It doesn't. The real explanation resides in understanding the energy diagram. So if you understand the energy diagram, then you have understood what is an impure semiconductor or a extrinsic semiconductor. Otherwise, you have not. So these electrons, because of the small gap, are able to go jump to the conduction band very easily. So that's your conduction band. Now you can see in the conduction band, you have electrons coming from two sources. One from the valence band of silicon. The second uh, place from where you're getting extra electrons is the donor energy level electrons coming from phosphorus, and they are also reaching the conduction band. Now you can see the conduction band suddenly is flooded with electrons. The and of course, one more thing happens, that as the silicon electrons reach back, electrons reach the conduction band through this jumping process. They leave behind holes. So this electron which is gone, now what it happens is it leaves behind a hole here. Okay, so the holes get created here. So if you notice in an N-type semiconductor, what's happening? In the conduction band, you have flooding of electrons. You have N-type semiconductor. I mean, N-type carriers, which is electron negative. And you have some amount of holes also. So in an N-type semiconductor, yes, it is very true that the majority charge carrier, that is when the current flows, majority charge carriers are definitely electrons. Okay, they are electrons. But if we talk about the minority, you still have some holes which are left back at the silicon level. So if you can see the silicon level in the valence band here, these electrons, when they leave, very few leave. Most of them actually come from this because they're easier. So the minority charge carriers are also there. Minority charge carriers are also there, and they are holes. So remember, when an N-type semiconductor conducts electricity, you have the charge, which is electron, moving in conduction band energy level, and the holes are moving in the valence band level. So the current in a N-type semiconductor is also due to electrons and also due to holes. But due to holes, it is very, very minor, and therefore it is ignored. But majority of the current is because of IN. So this is IH hole, this is IN. This is how a N-type semiconductor is able to have a lot of electrons. So the number of electrons is very, very large as compared to number of holes. One more important point, and this is the basic one, the level of doping which is done, that is the amount of pentavalent impurity that you add, is some millions. The ratio is 1 is to maybe 10 raised to power 8, or something like that. So this is one phosphorus atom, and these are silicon ones. So the ratio of doping, which is adding impurity, is, you can see it's very small, but the impact on electrical property, which means you create an N-type semiconductor which is now usable. Otherwise, just using intrinsic pure semiconductor is useless. But the moment you add this minor amount of doping, suddenly you get an N-type semiconductor, and you're able to use it for making electronic devices. I hope you enjoyed this video. Do not study semiconductor just at definition level. Go deep down inside energy diagrams. Only then clarity will emerge as to what is happening inside the semiconductor. I will come out with my next video on other topics in semiconductor. Until then, goodbye to you, and wait for my next video. Do not forget to subscribe to these videos, because the next video and the next video and the next video, I have 2000 already on my YouTube channel, is going to help you study at the comfort of your home. You don't need to go anywhere. That's a level of clarity that will emerge. Students who generally get selected or score marks are the ones who have clarity in physics. You don't need to study for 10 hours. You just need to study 1.5 hours of physics every day. But what you should strive for is clarity. And that is what my channel is going to give you. Thank you very much and wait for my next video.